Okay, let's start. So, hi everyone, I am João Borges. I am currently the chair of the International Younger Chemists Network. I'm very pleased to welcome you to this ChemVoices webinar on artificial intelligence and machine learning across the chemical science. And as you can see, we have really a great lineup of speakers from all over the world. Professor Pavlo Dral from Xiamen University in China, Professor Kulik from MIT in US, and also Professor Michele Ceriotti from EPFL in Switzerland. And we are really very happy to have you here. This is a very important topic for both the International Younger Chemists Network and International Union of Pure and Applied Chemistry. And together with my colleague, Eva, we'll guide you through the program, as well as present you with a brief introduction by the IYCN. Before that, so Eva, can you please just introduce yourself?
Yes, thank you very much, Joe. So my name is Eva van Dalen. I'm a PhD student in computational chemistry at the University of Zurich, and I'm head of the finance committee of IYCN, which next year will be the industry relations committee. Thank you very much for joining.
Thank you very much, Eva. So as I mentioned before going into the program itself, let me just introduce you briefly the International Younger Chemists Network, for those of you that are not aware of network already. So we are an associated organization of IUPAC since 2017, and IUPAC has been really providing us a lot of support, technical and logistically, in order to aid in our development over these last 5 years. And we have been also collaborating a lot with IUPAC on promoting joint goals, and we have worked also on several joint projects. In terms of our vision and mission, so the vision of IYCN is to connect and empower younger chemists globally, and the mission is to support and advocate for younger scientists working across the chemical science towards a globally sustainable future. So again, for those of you that are not aware of network, and if you are eligible or not to join, so we have a quite open eligibility criteria. So you can just follow in this link. It's free of charge, the membership, and if you are eligible, you will receive a lot of information by email on interesting opportunities for you to join several webinars, but also opportunities on projects to work on and to collaborate with us. And as soon as you are a member, you can also work within one of 8 committees of your interest that are listed at the IYCN website. So please have a look into this form and the website itself. And then if you have any questions, you can always email us at iycn@iupac.org. And apart from that, you can also follow all of our activities on social media. We promote everything in there, and would be happy, of course, to engage with you. And here we show a picture of our very first delegates assembly. It was in Paris in the occasion of the IUPAC World Chemistry Congress. Last year, we were supposed to have it in Montreal on the IUPAC Congress as well, but due to the pandemic, of course, everything turned virtually. So we met also virtually on the occasion. It was an opportunity to exchange with a lot of delegates from all over the world. And very soon we'll have our third IYCN General Assembly that this year will also take place virtually. So in terms of the ChemVoices project, so this is a joint project of IUPAC and IYCN, and you can get more information about the project, everything that we organized in the past in terms of webinars, by looking into the website chemvoices.org. And again, what we aimed in here at the beginning of this series of projects was to showcase the future of chemistry. So we organized a series of webinars in which we highlight the periodic table of younger chemists that have been awarded in between 2018 and 2019. And as you can see here below, we have organized several webinars already on different topics that are of interest to early career chemists, but also in general to the broad community, scientific community. So you can see some of them: Chemists Beyond the Bench, Resilience, Fostering Innovation through Collaboration. ChemVoices and the GWB also partnered in organizing this webinar on empowering diversity in chemistry, to highlight the work of women in chemistry as well, and to support them. And several other you can also see, they are always recorded, as this one is being recorded and will be also later on available at the IUPAC YouTube channel. This year, this ChemVoice series will be a bit rebranded, and will be also highlighting some IUPAC committees, divisions, and projects. So please stay tuned for the upcoming events that will be taking place in the sort of this ChemVoices webinar. So now, as I mentioned, so we have really a great lineup of speakers, and I am sure that we are here to hear from all of them, are their work and their groups, what they are doing in this digital chemistry and artificial intelligence and machine learning. And to do so, we have really a great program. And I will now hand over to Eva, that will please introduce you the program and then each of the speakers. Eva, please.
Yeah, thank you, Joe. So we will have 3 presentations of 20 minutes each, followed by a Q&A session. So please, if you have any questions, post them in the chats. We will collect all questions and then ask them to our 3 professors present here after the 3 presentations. So we will start with Professor Dral from Xiamen University on accelerating and improving computational chemistry with artificial intelligence and machine learning, followed by a presentation by Professor Kulik from MIT on what problems can machine learning solve in inorganic materials discovery. And then we are pleased to have Professor Ceriotti from EPFL Switzerland on blurring the lines between machine learning and quantum chemistry. So let's start by introducing our first speaker, Professor Pavlo Dral. So he obtained his PhD with Professor Tim Clark at the University of Erlangen-Nuremberg in 2013, followed by a postdoc at the Max Planck Institute for Coal Research with Professor Walter Thiel. He has been an associate professor since 2019 at Xiamen University and is now a full professor there. He is the founder of the ML Atom package for atomistic machine learning simulations and co-founder of the Xiamen Atomistic Computing Suite. He introduced and continues to develop several models within machine learning. He won a gold medal at the 36th International Chemistry Olympiads and many more achievements. So thank you very much for joining, Professor Dral, and the floor is yours.
Yes, thank you very much for the invitation. It seems to be a very nice initiative, and I really like that it's all open and you can download later and watch it. And most importantly, that it is for younger scientists. So I will try to explain what we are doing very, very broadly without going into details, but to show the essence of what we can do with artificial intelligence and machine learning in my field, which is computational chemistry. I just briefly introduce Xiamen because probably many of you are not familiar with where Xiamen is and what it is. So this is a small island actually. It has also part very well connected to the continental part. So it's both on the island and continental part, and it has around 2 million on the island. And it's very nice city with very beautiful campus at the university. So for Chinese people, it's very famous actually place. So they know what beautiful place it is, and it's very popular touristic destination. But also in chemistry, if you pay attention to the developments in different fields of chemistry, Xiamen University contributes a lot, and it's globally ranked as 1 percentile. So it's one of the best universities in chemistry globally. That's why I joined it, and what I'm doing is computational chemistry. This is my group, and since there are many younger people, I really would like to invite those of you who are interested in what I'm doing to apply and hopefully join my group. We are always looking for talented people from different backgrounds. So this is a short introduction. And now I will talk about machine learning in chemistry from some interesting historical perspective. So this is a very nice review by Gashtaig and Zupan. So maybe some of you know these names, maybe not. But this is a very nice review, and if you read this review, what was in the abstract, that they overuse application of neural networks in chemistry, and then application in spectroscopy, mass infrared, ultraviolet, and so on. So in many different scenes, right? And now the question to you would be like, what do you think, what year this review was published? Of course, I don't have here direct feedback from you, but that's something I love to ask audience. You can think about it. And here is the answer. The answer is that it was published in 1991, right? So the review in 1991 about something that we talk about now as a kind of a hot topic and something new, right? So it's not actually very new in a way that in science many things go like in a spiral, right? So historically. So the question is now, like, if it was already in 90s, apparently quite applicable to many problems in chemistry, why it's now becoming a hot topic, and what was before it became hot topic? And before that, it was actually pretty empty. So there was not much going on in chemistry using machine learning. There was some niche applications like in drug design. So if you go to look at the drug design, the neural networks and other machine learning approaches were used there for all this period, for structure, for QSAR, like structure activity relationships, structure property relationships. But if you look at computational chemistry or just chemistry, there was pretty big gap from 90s up to 2000, and it really started going on from, so there were more and more achievements and publications from 2010s, and now it's basically exploding, right? So what is going on here is very typical cycle of technology, and this is a very nice picture showing that this is kind of hype cycle, right? So that we what was before 90s and 90s, it was a kind of peak of inflated expectations. It was obvious that technology is great and it has big potential, right? But the problem was that we didn't have back then enough computational resources very well. So actually algorithms, as you see, like neural networks, backpropagation, they were pretty developed, like basic algorithms were developed. Now, like there are more advanced algorithms, but most of things were quite known, right? And the problem was really that the hardware and computational resources. So that's why there was travel disillusionments when it was not enough to actually make a big change in chemistry. And what we are doing now, we are entering the plateau of productivity where we actually use machine learning to do really new science, not just do science in old ways, but we can discover new relationships and make new discoveries in chemistry using artificial intelligence. Since I am working in computational chemistry, I'll just show how it changes computational chemistry, how it changes quantum chemistry, and the talks later will elaborate on. So they within the same lines. Actually, the last talk by Michele is going along the same lines, blurring the boundaries, right, between computational quantum chemistry and machine learning. So I will start with quantum chemistry. So basically, all chemical problems we have can be solved by solving the Schrödinger equation, right? And this Schrödinger equation has very simple form mathematically. The problem is the solution of it. But if you look at the equation, you have this Hamiltonian, which when you apply to a function, you get your energy or other properties. He is for energy, and then if you solve this equation like with some computational chemistry methods, then you get a pretty decent agreement with experiments, sometimes even better than experiment, depends on the problem. Like for example, take H2 bond. So very, very simple chemical problem, right? And I'm talking about this because it's very easy to understand and then generalize. So experimental bond length and like quantum chemical bond length is very similar. The problem is, even for such a simple molecule, it takes 5 CPU days to optimize the structure, which is quite a lot. And for real molecule, realistically, like bigger than H2, that would take you too much time. You cannot do this. What you can do, you can introduce lots of approximations. And this is what we were doing long time. And when we introduce approximations, we get lots of computational chemistry methods from ab initio to DFT and semi-empirical. This scheme is very simplistic, but basically, the more accurate the method is, the slower it is, right? So this is a very general observation. Now, with machine learning, we have a game changer because it can be as accurate as your best quantum mechanical method if you have enough training data, right? But it's much faster than any of these quantum mechanical methods. It's actually a bit slower than molecular mechanics, but on the same kind of scale. And you can also combine machine learning with the methods, and here is about this blurring the lines, and you hear about it in the last talk. And how we can blur the lines is actually so here. But before I talk, let's just show why we do machine learning, right? So it's not just on this plot it was not clear. So, but here, if you compare the time, so if you do very accurate calculations with quantum chemistry, then it takes for H2 molecule 5 CPU days. With machine learning, it takes less than 1 second. So it's extremely fast. And the reason for this is the difference between how we actually done quantum chemistry before. So we needed to really write equations and write the code for every property we want to calculate. Well, with machine learning, in principle, here is in principle because usually there are some other problems to solve, but in principle, if you have training data, you can use the same code and just learn these different properties, right? So this is the power of machine learning. Basically, given a data, it can learn many things, and it will be very general, so it's easier to use, and it's very accurate and fast, right? If trained properly. And we can merge machine learning also with quantum chemistry. So here, usually when we solve quantum chemistry, we can just learn the result of the solution of Schrödinger equation. But we can also learn Hamiltonian and then solve the equation, or we can even learn the wave function. So there is lots of potential and lots of interesting works which are now entering computational chemistry. And one of the easiest way to do it is basically take some very fast but not very accurate computational chemistry method. Like here is for UHF. So for those who know, it's not a very good method. You don't want to use it. Nobody uses it really for you either use DFT or some ab initio methods. But if you use UHF, you get some qualitatively correct, for example, dissociation curve of H2, right? If you use machine learning but train only on the part of this dissociation curve, then you will not be able to predict correctly the minimum. So it's very accurate for the training points, but it will be very bad for the other points. And one way is, of course, to cover all the points which are relevant, which is the very good strategy. And other strategy is also complementary strategy. It's not the other strategy, but a different way to do it is to learn the differences between the low-level and high-level methods with machine learning, and then you will be able to predict even the minimum correctly and preserve the physically correct behavior. Plus, you will be able to have a good accuracy too, because the difference is usually easier to learn. So we've done it actually for not just very simple molecule like H2, we've done it for different organic molecules and the distorted geometry. So we generated lots of data, and for this study we took already existing data, but it was almost 5 million data points and 5 different nuclear configurations of different molecules. And then we have also 500,000 of even more accurate data, and by some clever combinations of delta learning and transfer learning, we can obtain methods which have very, very high accuracy. We call it IYCN1, and the speed of the low-level method. And it's general, so it's not just applicable to H2 molecule, it's actually applicable to many different molecules. So if you look at this kind of simplified scheme of accuracy, computational cost, connection, and transferability, so you could see that IYCN1 is trying to approach the gold standard, very accurate method coupled cluster, while the cost is of low level semi-empirical methods, which are at the bottom end of accuracy in quantum chemistry, but they are fast. And if you look at the time, so this is time, and this golden method, so this gold standard method, just to run one simulation like 70 hours. It's not even a geometry optimization. With IYCN1 is 14 seconds on a single CPU. And if you look at the bond lengths, like for some data for which we have very accurate experimental bond lengths, you see that the agreement between experiment and our machine learning improved quantum mechanical method is very, very good. So this is the power of machine learning, and it allows us to do actually some new science. So for those of you who know about computational chemistry and density functional theory, so it's actually more IYCN1 is better than many popular DFT. So many people use B3, which is a kind of standard method for many calculations. The problem with it, for some complicated electronic structure molecules, it predicts even wrong geometry. After applying the IYCN1, you can get the correct geometry and also much faster. So this allows us to do some new science, because we can even resolve some structures which were problematic even for X-ray structure determination, which is experimental method. So it was known that from X-ray that the triple bond lengths in this kind of conjugated compounds with carbon chains, here they are too short. And with the IYCN1 we could see that actually we can get a much significantly longer bond lengths, which actually changes our understanding of these compounds. And then another contribution is that these methods are already accurate enough to target thermochemical properties, like enthalpies of formation or heats of formation. They are standard properties for chemists, and they determine how the reaction is possible to go or not. And usually we want to achieve something like 1 kcal per mole accuracy. And this is usually a problem for quantum mechanical methods. You need very accurate methods, but if you use very accurate methods, they are very slow. So with the IYCN1 you can get like fast and accurate, and plus as a machine learning method, it gives us uncertainty estimates. So something which is very important. When you know uncertainty estimates, so I will not go into detail, but you can basically look at the deviation of predictions of different neural networks. You can predict which calculations are not very confident. And if they are not very confident, if you exclude them from statistics, then mean absolute errors for different data sets actually goes to below 1 kcal per mole for many data sets, which basically reaches chemical accuracy. So it's a great achievement, but it's also interesting to look at the calculations which machine learning is confident about. And for these calculations, we can compare to some other high-level quantum mechanical calculations without any machine learning. And if the agreement between them is good, but they disagree with experiment, like for this molecule, then probably something is wrong with experiment. And then we found in the NIST database a corrected value for some of the heats of formation, so which shows that with machine learning we are at the stage that we can even find some problematic experimental results. So this is really very encouraging. And all this stuff you can do already online on the cloud, so you can run these calculations on the web. So you don't need to be to install anything or be specialist in it. And like there are some other capabilities which so we do it with a Miliatom package on the Xiamen Atomistic Computing Suite cloud computing service. So you can do it. I will not talk. So I will finish because I'm running out of time. I just want to finish with a statement that basically machine learning is here to stay, and it's not a passing fad. It's already permeates quantum chemistry, computational chemistry. If you want to learn more about it, you can learn from different resources, like from this website. You can go to the conference about it. Will be next year in Uppsala. And there is even a book about it, so you can check it later. And with this, I want to thank everyone, and I'm looking forward to your questions.
Thank you very much, Professor Dral, for this very interesting talk. So again, questions can be asked after the talk, so you can write your question in the chat, and then we will pose them in about 40 minutes. So next, we will have a very interesting presentation, I'm sure, from Professor Heather Kulik from MIT in the USA. Professor Kulik obtained her BE in chemical engineering from the Cooper Union in 2004. Then she did a PhD with Professor Nicola Marzari and the Department of Material Science and Engineering at MIT, followed by 2 postdocs at the Lawrence Livermore Lab and Stanford University with Professor Lightstone and Professor Martinez, respectively. She is now a tenured associate professor at MIT and has won a great number of prizes, including the Burroughs Wellcome Fund Career Awards at the Scientific Interface Office of Naval Research Young Investigator Awards, DARPA Young Faculty Awards, and many, many more. So I'm looking forward to your presentation. Thank you.
Thanks. Okay, so I think the previous talk gave an excellent introduction to what I'll talk about, and I'll just dig into one part of our research. But as was mentioned in the previous talk, you know, machine learning's been around for a while, but the challenge is to think about how to use it and how to integrate it into computational chemistry. And the specific area that my group focuses on is challenging open shell transition mal complexes, where sometimes the tools that work well for the organic systems you saw previously tend to fail. And this failure can both be on the machine learning side as well as on the first principles modeling side. But today I'm going to give you a sense of some of where I think we can start to overcome these limitations to really accelerate the discovery of new materials. And so if you're not familiar with our approach, we really work through this general way of first we built tools to automate the structure generation and screening of transition mal complexes. We've built machine learning models that then predict DFT quality results. We use these types of models in combination with evolutionary algorithms to go out and accelerate the discovery of new materials in large spaces of compounds. And we try to interpret why the models are predicting the materials to be lead. So what particular aspects of the model are leading to certain types of property predictions. And an example of this is that we're able to come up with new leads for a design challenge such as redox flow battery, redox couple design in a handful of weeks, as opposed to decades that we would require for random search, by rapidly screening through a space of a few million compounds. So I'm going to come back to that in a moment, but just giving you a sense of a bird's eye view of how my group is integrating machine learning into workflows. And now let's dig into some of the technical details. So one of the key things that we do that's a little different from most of the organic chemistry community is we work with smaller data sets of open shell transition mal complexes, and we know that the things that matter most about a transition mal complex are really focused towards the metal. So we devised a series of graph-based descriptors, and these graph-based descriptors give us a chance to inform the model about what matters most about a transition metal complex. And these are products and differences of heuristic properties on the molecular graph. And so we describe a series of bond paths of walking through the molecule without providing any geometric information, and this is what they look like. The heuristic properties we use in these racks can be more electronegative in nature. So nuclear charge, electronegativity, we'll call those electronic properties. Covalent radius, topology, and identity are more geometric properties. And these are just heuristic properties that come from a lookup table. So we're preserving the accelerations and speedups that you saw in the previous talk. And the result is that we're able to achieve accuracy on the scale of to within the ground truth of DFT, about 1 kilocal per mole mean absolute error, or 1.5 kilocal per mole root mean squared error. So this is with respect to a single DFT functional ground truth. And on the same small data set sizes we tend to work with, so we work with on the scale of a couple thousand points, we achieve accuracies up to 15 times higher, just simply by encoding this information about what matters most about a transition metal complex. And so I'm not going to talk too much about that today, but just to say, as I mentioned, one of the most important things about this is, can we interpret why the models make the prediction they do? So we tend to work a lot with different estimates of feature importance. And so here I'm showing these as pie charts. The pie charts of the selected rack features in a kernel-based model are the ones that are most important to making the prediction, and they tell us why the models make the predictions they do. And so on the left, I'm showing a pie chart for predicting the spin of a transition metal complex, whereas on the right, I'm showing a pie chart for predicting the redox potential of a complex. And so now I'll show this in a little bit clearer visual way. So again, what we're doing is we're applying a procedure called random forest ranked recursive feature addition. And so in that way, we pre-rank the features with a machine learning technique known as random forest, and then we add them sequentially into a kernel ridge regression model. If the feature improves the model performance, we keep it. If it doesn't, we throw it out. And the result is that we can then go ahead and look at an abstraction on a porphyrin of the most important features for predicting a property. And here I'm going to color these properties electronic. I'm going to color the more electronic properties blue if they matter more, yellow if geometric properties matter more, and I'm going to make the atoms big if they're important in the prediction and small if they're unimportant. And this is shown on a porphyrin, but it's representative of our data sets of a few thousand transition metal complexes. So if we look at what it takes to predict the spin of a transition metal complex, we can see it's extremely metal local in nature and focused really on the electronic properties of the atoms directly coordinated to the metal. And the difference between this set of 41 features versus this set of 26 features is just a tighter cutoff on the random forest aspect of the recursive feature addition. Where this gets interesting is when we contrast this observation with other properties, such as what does it take to predict the metal ligand bond length? That turns out to be a much more overall property of the molecule. So it's not just what is coordinating the metal in the bond that predicts the bond length, but also the sterics of the atoms around that bond. And then redox lights up an entirely different part of the molecule. So this suggests to us that if we want to design the redox potential of a transition metal complex, we can tune atoms far away from the metal. And if we want to independently design the spin, we can tune atoms close to the metal. And so these are the pie charts I was alluding to. The pie charts here for spin show much more blue, red, and green, which means that they're much more metal local in nature. And when we see a lot of gray in the pie chart, that means there's a lot more non-local information. But everything I've described to this point relies on one single DFT functional. And so a big challenge we wanted to overcome and address is when we're relying on a single DFT functional to accelerate discovery and build these models, how much bias are we inheriting? So we went back to one of the properties we predict the most, which is the adiabatic high spin, low spin splitting. This is a very challenging property to predict from DFT. And my student Chen Ruduan, who's actually defending his thesis today, went back and repeated all of the calculations with 23 different density functionals spanning what's called Jacob's ladder, from semi-local GGA functionals all the way up to double hybrid functionals, which we would expect to be more accurate. And what we find is that there's very good correlations between different density functionals, even among those that we would typically think to behave differently. So for instance, the meta-GGA TPSS and the GGA BLIP have extremely good correlation, and even cases where the methods tend to disagree, such as this Minnesota style M062X and BLIP, there's still a lot of structure in the data. So we're interested to know, where do functionals agree and disagree the most? We can compute a standard deviation among all the functionals to see which compounds do we have the greatest density functional agreement or disagreement. And what we saw was that, in general, somewhat disappointingly, when the intermediate field strength is present, which would lead to near degenerate high spin and low spin states, the functionals tend to disagree the most. The functionals agree really well when we're either in the limit of low spin or high spin. And so the result is that if we pool together all the semi-local functionals or all the hybrid functionals and aim to predict what makes a spin crossover complex, which we define as a complex with near degenerate high spin and low spin states, then we see that there's relatively little consensus on what it takes to make one of these materials. It's harder to get all of the functionals to agree on what it takes to make a spin crossover material. And this is really a property dependent observation, because if we instead look at what it takes to get functionals to agree on the HOMO-LUMO gap, we see much better consistent agreement. So the degree to which different exchange correlation functionals agree is really sensitive to the property. But the other thing I mentioned is that, one of the greatest things we think we can do is build these interpretations of what our model is learning and why. And so I'm taking us back to those pie charts I showed earlier. This is the high spin, low spin pie chart for BLIP functional. And here I'm showing HOMO-LUMO gap for vertical ionization potential. You can see the HOMO-LUMO gap and vertical ionization potential are much more dependent on local information, and so have much more gray in the chart. And we can look at how these pie charts change as we change the functional. So we can contrast BLIP with functionals that had relatively weak correlation in the properties with BLIP, such as the M06L functional or M062X functional. And we can even introduce a double hybrid, like PB0 double hybrid, which we think should give more accurate property predictions. And what you should notice is that the pie charts are actually changing very little as we change the functional. There's much more difference between the top row of the high spin, low spin pie chart versus the HOMO-LUMO gap or vertical ionization potential. So what this tells us is that we can obtain the pie charts at the GGA level of theory, but then use them to guide inquiry and scientific study at a much more high level of theory, such as the double hybrid, and that ultimately we can use these techniques to get a path to universal design principles that doesn't require high computational cost. And I don't have time to talk about it, but we also showed in this paper that the same observations held if we change the basis set and so on. So the other thing we can do, now that we have 23 different neural networks, now that we have 23 different density functionals, we can try in 23 different neural networks and go out and explore a space of 187,000 candidate materials and ask, when do at least half of the different density functionals agree? And because we looked at such a diverse array of different functionals on different rungs of Jacob's ladder, this requires that at least some of the rungs agree. And so here I'm visualizing the latent space, the 187,000 compounds in the latent space of our model. And this is where our consensus approach agrees that all of the different spin crossovers, which again are high spin, low spin, near degenerate states, would reside. If we instead did this with a single functional, such as B3LIP, we get a much bigger area of the space being picked out as being a candidate for spin crossover. And then the last thing we can do is we can mine the experimental literature for mentions of spin crossover in the experimentally known compounds and place those in the same space. And this is what we get. And so while it's not guaranteed beforehand, we can see that by requiring the different density functionals to agree, we are more robust at predicting where experimentally known compounds are. And what this allows us to do is it allows us to propose new materials that haven't been studied as much experimentally. And in particular, it suggests that experimentalists should explore more cobalt nitrogen compounds than have been previously explored for spin crossover. So now I want to come back in the last part of my talk, I want to come back to this question of how do we actually accelerate discovery? And I'm going to bring you back to the example I was showing on my first slide. And we were interested in understanding how to tackle the design of redox couples for redox flow batteries. And so to make a good redox couple for a redox flow battery, you want to maximize its solubility in polar non-aqueous electrolyte. You want to maximize its redox potential, and you also want to keep it from decomposing, make sure it's stable and resistant to crossover. And some of the most well-known redox couples for redox flow batteries are these vanadium ACAC complexes, but we're interested in exploring new designs that hadn't been studied before. So to design a redox flow battery redox couple, we really need to balance three outstanding challenges that I just mentioned. And the way that we address the stability and resistance to crossover question is we built a candidate pool of new materials, starting with synthetically accessible heterocycles, fusing them together, adding functional groups to potentially tune other properties of the transition metal complex, and we combine them with 4 earth-abundant metals that had promise as redox couples but had been relatively underexplored. If you just multiply these numbers together, you come up with 2.8 million candidate bulky homoleptic transition metal complexes. Now, these are much bigger. They're about 100 to 200 atoms in size, so they're the types of complexes that would take days to weeks to optimize with DFT, and they're much bigger than anything we'd ever studied before, so we had no real data in the group to help start off any machine learning models. So rather than pre-training a machine learning model and doing this optimization, we used an active learning approach where we combined uncertainty quantification with the efficient global optimization algorithm to go out and explore the space. And I'll show this as a cartoon on this slide, and then I'll show it with real data on the next couple of slides. So we optimize solubility by optimizing the log P and the redox potential. We go out and we collect some DFT data. We can then train a neural net and ask the neural net, what do you think of these 3 million compounds? Then what we do is we look at the explicit points and form a Pareto front, and then predict with something called the 2D expected improvement criterion how likely and how uncertain is it that these points will reside beyond the Pareto front. This allows us to pick out new candidates, and then we go back to DFT. We revise those points, and then we retrain our model and repeat. And so this is what it looks like in practice. After about 2 weeks with DFT, this is all we've got. We've got a handful of points. But with a few minutes with the neural net, we can get a prediction of the entire space. We can pick out the compounds that seem most promising to go beyond the Pareto front, and we go back to DFT. We can see the neural net was not that smart yet about what the space would look like. So we go back to the neural net again, we retrain it, and we pick out new candidates, and this time we do much better. So after another week with DFT, we have that many points, and then a few more minutes with the neural net, and we repeat this process again until after about 6 weeks with DFT, we can see that the neural net is saturating its opinion on any of the points continuing to improve. So the EI score that used to be yellow on the front is now turning blacker and blacker. There are fewer points that are going to improve beyond the existing Pareto front. And so after about 15 minutes with the neural net and 6 weeks with DFT, we decide to stop and take a look at what the leads are on this Pareto front. And all of these points really reside in the last few generations of the optimization. And in general, if we're interested in maximizing redox potential without sacrificing solubility, what we find is that these manganese high spin complexes with oxygen in the ring and sulfur in the ring are really the optimal design. And a conservative estimate is that we did at least 500 times faster than random search. And 500 times faster might not sound too fast, but you realize that this was done with high throughput DFT with parallelization on 64 GPUs. And so you can see this is the difference between having an answer in about a month's time versus not in our lifetimes once you work through the math. And so we could go back and take a look at things like catalysis. So we could look at a reaction my group studies a lot, which is the direct conversion of methane to methanol. And we could simultaneously optimize for this rate determining step, the hydrogen atom transfer step, as well as the release of the product. And we searched a space of 16 million candidate catalysts, stitching together different heterocycles to form common macrocycles, including ones that are synthetically accessible, as well as ones that that had never been synthesized before. And we can do the same thing where we optimize for different generations. And the final result is we observe that, for instance, new features such as anionic ligands in the axial position are really important for facilitating methanol release. So I just want to finish by pointing out that there is one dark side to allowing machine learning models to set up all your DFT calculations, and that's that a lot of times we want to set up a certain type of calculation, but then we get something that fails. And so we would like to be able to distinguish and predict beforehand what will lead to a good DFT calculation versus what will lead to a bad one. And so we actually built neural net classifiers that could predict with 88% accuracy what would lead to a good calculation versus a bad calculation. But that requires that you go out and seek training data of what makes a bad calculation. And then when you go to a new chemical problem, the accuracy of the models will erode. So we devised an uncertainty quantification metric to improve upon this, but we wanted to do this another way. So what we did was we devised a strategy for what we call in situ calculation monitoring. And so we specifically extract properties that are computed at each time step in an electronic structure problem, and we pass them to a convolutional neural network, and we actually predict the likelihood of a calculation to fail, feeding the model more and more information during the optimization. So we take just the beginning part of the optimization, but the more of that information that the model has, the better it is at predicting if the calculation will fail. And we extended this to the catalysis problems I hinted at earlier. So we applied it to the full catalytic cycle of methane to methanol conversion. We were able to train it only on just one intermediate, the metal oxo, and then apply it to all the other intermediates. We also could do things like change the metal of the catalyst. Because we're using electronic structure descriptors, the model is very transferable. So across all sorts of different diverse chemistry test sets, we're able to achieve good accuracy, and the accuracy that increases the more information we have about how many geometry optimization steps that have been carried out. And the result is that we're able to save all of the time wasted on bad calculations with very few false negatives. And if we interrogate why the model makes the predictions it does, we can see that it's because when geometry optimizations fail, they tend to lead to wiggles in the end of a geometry optimization in properties, and those wiggles are more transferable than the raw properties or the chemistry of the transition melt complex itself. So I think I'm about out of time. I'll just finish by saying I started by telling you a little bit about what we've done in high throughput transition melt chemistry and machine learning property prediction. And these tools are really useful for thinking about accelerating discovery, and at the same time it mandates that we think about smarter ways to automate our calculations. Everything I've talked about today is available in our open source code, as well as a web interface. And I'd just like to finish by acknowledging the students who did the work. Most of the work I told you about today was done by Aditya Nandi and Chen Ridwan. And thanks for your attention.
Thank you very much, Professor Kulik, for this interesting talk. So as a third speaker, we have Professor Ceriotti joining us from EPFL Switzerland.
Hello?
Yes. Okay, we can hear you. Perfect, thanks. So Professor Ceriotti obtained his PhD in physics from ETH Zurich, then was a junior research fellow at Merton College at Oxford University. Currently, he is associate professor at EPFL. He is leader of the Laboratory for Computational Science and Modeling at the Institute of Materials at EPFL since 2013. He's also an associate editor of the Journal of Chemical Physics and moderator of the Physics Chem section of Archives. He has won several prizes, including the IBM Research Forschungspreis, the Volker Heine Young Investigator Award, has an ERC starting grant and also received an ERC Consolidator grant, and many more prizes. So thank you very much for joining us, Professor Ceriotti, and I'm looking forward to your talk.
Thank you. Now let's see if I can share the screen. Do you see my screen?
I don't see it yet. I'm sorry. Yes. Okay, I can see your screen. Perfect. Thank you.
Do you hear me?
Yes, I can hear you.
Okay, awesome, because I have a rather complicated setup here. I'm speaking on my phone and showing the screen from a virtual machine. So thanks a lot for the very kind invitation, and thanks also to Pavlo and Heather for setting so nicely the stage and introducing a little bit the why we're doing this and what we can achieve. So I wanted to get a little bit more technical in my presentation to give you a little bit an idea of how, from a conceptual and also a practical way, machine learning for chemistry is evolving to be something more than just throwing data at general purpose algorithms, but is evolving to include more and more insights about the physics and the chemistry that drive the behavior of molecules and materials. So the general idea of what we are trying to achieve is pretty much what has been set out so nicely by Pavlo and Heather. But in particular, I want to focus on a specific flavor of machine learning for chemistry that involves essentially building surrogate models of quantum mechanics. So the idea really is that every property that can be computed by quantum chemistry, and as Pavlo has shown, you can actually use very high levels of quantum chemistry, so that in the end you can get the machine learning models that are more accurate than DFT. And you can use these surrogate models to predict the interatomic potential energy, which is what you need to determine what is the stable structure of a compound. But also, and this is something that I will discuss a little bit more today, you can also predict all sorts of functional properties of materials and molecules, dipole moments, charge density, Hamiltonians, that are important because they allow you to predict the outcomes of experiments and optimize the functional performance of a certain compound, and also allow you to build modeling frameworks that are kind of in between chemistry and machine learning. So from a mathematical point of view, when we look at molecules from the point of view of performing a machine learning prediction, you can look at a molecule as a point cloud. Essentially, each atom is characterized by its Cartesian coordinates and by its chemical nature. Now, there are two equivalent but alternative ways of looking at a point cloud. One is basically looking at the point clouds as a collection of points and the labels associated with each point. The other is looking at a molecule as the connectivity, as essentially a graph. And both these mathematical viewpoints have been used a lot in the context of chemical machine learning, and actually, as I will show, can be combined within a single conceptual and mathematical framework. So let's say that we want to map the structure of a molecule as characterized, for simplicity, let's say, by the nature of the atoms and their positions, and you want to map it onto a set of properties of these molecules, the potential, the dipole, or whatever you need for your application. So this mapping should satisfy some requirements that are basically set by the physics of the problem. So for starters, you want this mapping to be smooth, because as you move atoms smoothly, all the properties that you can predict by a quantum mechanical calculation, at least in ground state setting, will vary smoothly. Meaning that, for instance, as I move an atom, there will be a finite smooth derivative that determines the force, and as as we move an atom, the dipole moment will change in a way that is determined by the sensitivity matrix, and so on and so forth. Another requirement, which is pretty obvious, but actually is not at all easy to implement in practice. And actually, if you like mathematical puzzles, these are two references by an excellent PhD student of mine, Ceriotti, that show you how this is far from a trivial thing to ask. And what this trivial requirement would be to have the mapping to be complete. So essentially, we want that if we have two structures that are distinct, it should be possible to predict the different values of their properties. And what makes it hard to, and together with this requirement of completeness, another common requirement is that of having a description of your system, a model that is additive in nature, essentially meaning that the properties of your compound are built as a sum of contributions that are associated with atom-centered environments. And this is important because this basically is the mathematical structure that allows you to build predictions of complicated systems using simple enough building blocks so that you can learn them using high-end quantum chemistry methods. And last but not least, and this is actually what makes all the other requirements not so trivial to fulfill, it's often very useful to have a mapping that is symmetric, meaning quite trivially that if you consider two molecules that differ only by a rigid translation, a rigid rotation, or the labeling of the atoms, basically the order by which you consider the different atoms, their properties shouldn't change. And actually, these physical requirements on the mapping between a structure and a property affect the mapping between a structure and the model that you use to describe that property. So, for instance, if you want to have a model that is able to predict the properties in an additive fashion, this model should be itself built around the description not of the molecule as a whole, but as a description of atom-centered environments, so that then you can build the final property of your system as a sum of contributions that come from each individual atom-centered environment. Now, I want to stress here, this doesn't mean that you need to define atom-centered properties to use as targets. You can learn the total energy or the total dipole of a molecule, just you formulate the model in such a way that the ansatz that you use is built as a sum of atomic contributions. When it comes to symmetry, requiring that the mapping between structure and properties is symmetric implicitly requires that the model is symmetric, meaning that the functional form that you write when you implement your model shouldn't change its outcome if you rigidly rotate the atoms, for instance. More generally, if the property that you're trying to predict is a vector, for instance, or a tensorial property of arbitrary order, you want this mapping to be equivariant, meaning that basically when you predict, for instance, the dipole moment of the rotated version of a molecule or an environment, this prediction should naturally and automatically be the rotation matrix applied to the dipole moment of the unrotated environment. This equivariant property is what basically makes sure that the structure property mapping is itself fulfilling all the symmetries of the physical system. Similarly, if you want your predictions to be invariant or equivariant with respect to the labeling of atoms, this imposes constraints on the functional form that you use to build your models, which shouldn't change the value it predicts if you just provide as inputs the atoms in a different order. Now, it turns out that introducing these physical requirements restricts greatly the functional forms that you can consider. And actually, over the past 3 or 4 years, we have been able to construct a general formal theory of the construction of machine learning models for molecules that shows that these symmetry constraints effectively tie your hands, and pretty much all the major frameworks can be understood in the same framework as describing atomic environments in terms of correlations of the atom density. So, for instance, you might be familiar with the pair correlation function, which is something that you measure when you measure diffraction from disordered systems such as liquids. Actually, you can regard this pair correlation function as the symbol of a hierarchy of density correlation descriptors that provide, if you consider the whole hierarchy, a full description of a geometry of a system that is invariant to the absolute orientation of your molecule or material in space. And actually, this framework, as I anticipated, can be generalized. You can generalize it to build equivariant frameworks. So basically, build descriptors and models that are suitable to describe vectors or tensors of arbitrary order. You can use them to describe not only local, but also long-range interactions. This is something we are working on very actively, and you can have a look at these paper to have a brief introduction to how this works. But what is nice is that you can easily incorporate a description of long-range interactions also into this atom-centered framework. And finally, very recently, we have been able to show that also message passing neural networks, when you require them to be equivariant with respect to rotations, can be formally understood in terms of this hierarchy of density correlation features. So what can you do once you have incorporated all these symmetry and physics related requirements into your model? So essentially, what I think that you can do and what I think you should do is go all in and don't use only your machine learning model as a replacement for the interatomic potential, but use it as a replacement for any property that can be predicted with quantum chemistry. So, for example, you can use it to predict scalar properties associated with individual nuclei, such as NMR chemical shieldings, and have an ongoing collaboration with Lyndon Emsley, also at EPFL, who is an experimentalist as one of the world experts in solid-state NMR. And essentially, we showed that it's possible to build machine learning models that are as accurate as DFT, if not more accurate, and that are thousands of times more efficient, which allows you to do much more things than what you can do just by brute force electronic structure calculations. And as I anticipated, being able to predict the tensors of arbitrary orders allows you to do much more than just predicting scalars. So, for instance, you can predict the polarizability of molecules. And thanks to this additive structure, you can achieve a prediction accuracy with respect to post-Hartree-Fock methods that is better than the accuracy of density functional theory. And also, I want to point your attention to the fact that since we predict the polarizability as a tensor, we find, as it should be, that, for instance, if you have a conjugated system, the polarizability is much larger in the plane of the molecule than in the orthogonal direction. And having a fully equivariant model basically allows you to incorporate these basic chemical intuition automatically into your model just by targeting the total polarizability of a set of molecules. Now, you can also predict more complicated properties. For instance, you could predict the electron charge density. This is a direction which I've been working on together with Clémence Courmin-Boeuf, also at EPFL, and she has also extended these to predict all other sorts of scalar fields. And you can even go further and use this framework to predict molecular Hamiltonians. And what is very nice about predicting molecular Hamiltonians with an equivariant framework is that the model essentially knows about molecular orbital theory. And this is, I believe, a very cute example of what I mean. This is basically a toy example in which we try to learn the Huckel Hamiltonian for benzene. So basically, these are 30 times 30 matrix that describes the electronic structure of benzene in a minimal orbital basis. And we use as targets a matrix that is symmetric but is otherwise full of random numbers, literally numpy.random. And so when you try to learn this matrix of random numbers using an equivariant model, you just can't learn it. And this is not because of a limitation of the model. This is because no physical model of the electronic structure of benzene can avoid fulfilling basic symmetry rules. And so the Hamiltonian that you can predict after you trained it on this matrix of random numbers has a lot of structure because basically it's consistent with the D6H symmetry of benzene, even though we have not explicitly told the model that benzene is D6H. Also, the symmetry of the molecular orbitals and their degeneracies are fully consistent with what you would expect from molecular orbital theory. So what I think is now the next step in this integration of machine learning and physics-based modeling techniques is actually to combine thermodynamic sampling using machine learning potentials and the prediction of functional properties, which means that you can perform the kind of calculations that you usually had to do with ab initio molecular dynamics using a fully integrated machine learning framework. For instance, you can study ferroelectricity, here the paradigmatic example of barium titanate, by predicting both the potential and the polarization using a symmetry-adapted machine learning model. You can incorporate electronic excitations, for instance, in the prediction of the thermochemistry of a material. This is the heat capacity of nickel, and this is a picture that contains so much physics. So at low temperature, you have the deviation of the heat capacity from the Dulong-Petit limit, and this we can describe using integrals because we have an inexpensive machine learning potential. But if we go to high temperature, a machine learning potential is not enough because also the electrons start getting excited. And so here we add as a post-processing a correction that is based on the prediction of the electron density of states, and it allows us to estimate the electronic contribution to heat capacity and bring us closer to experiment. And finally, this is a very nice collaboration with Volker Deringer and his group. And this is a study of silicon at high pressure. And this is just to show you how, by combining machine learning potentials and the model of functional properties, here specifically the electron density of states, you can study systems with hundreds of thousands of atoms for tens of picoseconds in a way that is completely affordable, without having to burn your supercomputing budget for the next 10 years. Another example here is the prediction of vibrational spectroscopies in this case from liquid water. And again, here we're using a machine learning potential to describe the energetics, and also machine learning models to predict polarization and polarizability, so that we can predict using physics-based velocity and dipole and polarization correlation functions. We can predict the fully anharmonic quantum vibrational spectra of liquid water, and these are calculations that people used to call heroic. And basically now we can run these on our workstation without even using a high performance system. So as I said, the objective, in my opinion, is really to try and blur the lines between machine learning and quantum mechanics, because at the end of the day, even when you use quantum mechanics, you do a computational prediction of the properties of a molecule. And so why not mixing and matching machine learning and physics-based steps? And I have an example here for which I have just a preprint, where we study the properties of hydrogen at giant planets conditions of 50,000 Kelvin kind of temperatures. And here we don't only include the electronic excitations as a post-processing step, but we predict and use to propagate molecular dynamics defining temperature, electron free energy. And we do this not by learning directly a temperature dependent property, but by learning ground state properties, so the ground state energy and the ground state electron density of states, and combining them with a physics-based and completely inexpensive expression to predict the property that then we use to simulate the system. And so you can compute the corrections to the equation of states of hydrogen at very, very high temperature, using basically this combination of machine learning predictions for the ground state and basic physics formulation of the electron free energy. So to sort of wrap up and give you an idea of where we want to get, I think there are really two directions in which, as a computational chemist, one can approach machine learning in a way that doesn't, betray your training as a chemist. And one is, trying to stay away from ready-to-use machine learning models, that you just take it and use it, but try to understand what are all the pieces that build up a good machine learning model of the properties of a molecule, and then put them together in the form that suits best the type of problem that you're working with. So do you need long-range interactions? Do you need tensorial predictions? What kind of interactions? How transferable do you need to be? And so on and so forth. So I just want to point you to a set of open source tools that we have been working on that implement all of these ideas. And these tools are basically built in a very modular form, because modular is the understanding of the problem that we're trying to develop. And so we are trying also to develop a modular framework from the computational point of view. And finally, one aspect that I think is really the next frontier, and something that we are working on, but it's a little bit more at the speculative level, is combining theoretical and experimental predictions to exploit the fact that theory allows you, as Pavlo has shown, to get consistent results that, with some caveats, are internally consistent, even if not the ultimate physical reality, with experimental numbers that sometimes can have a little bit of heterogeneous quality, but are, at the end of the day, the ultimate benchmark of accuracy. So with this, I want to conclude, show you at least once the faces of the people in my group who did all the work that I showed you. And I leave you with a link from which you should be able to fetch this presentation. And I think that this we can, I thank you for listening, and I think we can switch to the question and A. Thank you.
Thank you very much, Professor Ceriotti, for this interesting talk. So now we will have the Q&A session. If you have a question, please write the question in the chat, and then we will collect all questions and ask them to the speakers here. Now, I would maybe start with the most often, the question we got most commonly during the registration, and it was, how can I learn machine learning? Do I need a background in computer science, or which sources, which steps would be best to learn machine learning? Maybe Professor Dral, can you start?
Yeah, it's a good question. It depends maybe what you want to do. So the most importantly, because as Michele said, that for different questions you need a different tool. So that would be general answer. And more practical answers, I showed you even in my slides. We will publish a book in 1 month, and there are some other books published specifically for physical chemistry and chemical physics. So something that is relevant to most of people who want to use machine learning in chemistry. So, and also HISA published, I think, a book in ICS focus, right? So there was also introduction of machine learning. So that would be a nice way to start, just from very general introduction, and just then see what tools are more appropriate, because usually these books have some introductory chapters about standard algorithms like neural networks, scalar methods, and so on.
Thank you. Professor Kulik, do you have any tips for beginners?
Yeah, so I think as Pavlo mentioned, there are a couple of books, but at least in the US, increasingly new faculty are hired in this general area and are teaching data science classes. So I think between the classes that maybe at your local institution, as well as online resources from those classes, if those classes are put on YouTube and things like that, those can also be good. You know, I think you can also start with more transparent and easy to understand aspects of ML and dig into the less transparent, say, flavors and neural nets later. I think you'd be surprised how much you've already essentially learned when you learn regression and things like that. The extensions to, say, other types of regression, it's not a huge leap.
Okay, thank you. And then a quite related question is which software is mostly used to do machine learning, and also in which programming languages are these software most commonly written? So I don't know if Professor Ceriotti can comment on this.
So I think that probably so you really have, I think, two families of methods. So the very early developers, so Beller or Gabor-Chani, used very traditional Fortran code. I think that the vast majority of recent developments, at least on the user-facing side, is just Python. Most of the work that I've seen is actually PyTorch. So understanding some Python and some Python dialects is probably the most useful way to invest your time if you are completely new to programming, also because it's probably the easiest. And then, you know, once you get more interested, and perhaps if you want to do more development, then also getting to learn a little bit of C++ is probably not bad. And I think that the same, I think that also on the previous question of what you need to learn, there is a big difference if you are interested mostly as a user, in which case I would say just go and learn linear algebra, because you will understand 99% of what you need to understand, as Heather was also saying. A lot of recent developments are based on equivariant machine learning, and this basically, you basically have to go freshen up your angular momentum algebra, and that's all that there is to it.
Okay, thank you. Any more comments on this?
Yeah, actually, I completely agree with Michele that I myself, when I started 2013 writing my program, it was in Fortran. Now, I mean, we are mostly switching to Python too, and we have some connections to Fortran. Yeah, it's the easiest way to use. Just also very popular TensorFlow. Also, for many students, it's one of the easiest, and they just try to use. And usually, it's you don't need. If you have some background in any programming, then you just can very easily start with using TensorFlow or PyTorch, and there are many web resources how to use them. So yeah, it's quite easy now with all the web resources.
Okay, thank you. Then there was a question specifically for Professor Kulik. Did you calculate any bioinorganic compounds?
So we do have extensions of everything I talked about over to thinking about the relationship to metalloenzymes, but nothing ready for prime time yet. But yeah, that's a natural extension, is thinking about how this works in proteins as well, since many of them are contain that bioinorganic motif.
Okay, thank you very much. Then for Professor Dral, can IYCN be used for reaction mechanisms and selectivity exploration as well?
Yeah, it should be usable. We actually use it now for locating transition states, and basically, if you know transition states, you can understand the mechanism and predict what you want. Yeah, so for selectivity, if you calculate the appropriate reaction pathways, you should be able to get this.
Okay, thank you. Then also, can you describe best practices in generating machine learning data sets? So the collection of the data and also the managing of the data, how to organize it and work with lacking data. Perhaps Professor Ceriotti, can you comment on this?
Why not? So it's actually, you know, Pavlo might have made it look easy, but it's not easy at all. Also, because there are at least two reasons. So one is that you need usually a much higher level of convergence of the basis set if you are in a condensed phase, k-point samplings. So your simulations need to be extremely consistent internally. Because otherwise you have small differences that don't matter if you are just studying one family of compounds, but matter a lot when you try to put together a very heterogeneous and diverse data set. And the second aspect is that, at least in my experience, you usually want, and this is something that also not myself, but also others keep finding over and over again, it's very important to also have structures that go a little bit outside your comfort zone, because you want your model to be stable also when you try to predict very distorted structures or compounds that shouldn't be stable. Your model doesn't know it unless it is exposed to it. And so I think that that's another aspect which people tend to underestimate. And in my personal opinion, one very pragmatic way, if you just need to solve a problem, if you don't need to generate a data set to be used for benchmarks or to be used by others and until the end of time, if you just need to solve a problem, active learning is a very good strategy to follow. So basically you start with a small data set and then you start doing whatever you want to do using some kind of uncertainty estimate to tell you when your predictions are not reliable and when you need to add more configurations.
Okay, thank you. Are there any comments?
Yeah, I just agree again. So I made it indeed a bit too easy, but it's a big problem because data determines at the end the quality of your machine learning. So, yeah.
And for people who are just starting with machine learning, are there publicly available data sets which are good to start? Yeah.
So we've dealt a lot with questions of data quality. One of the things I didn't have a chance to talk about is we've directly machine learned on experimental data, and that can introduce uncertainties because you're pulling data from many different labs. But in terms of data management, within my group, we use Mongo databases to store data and attribute metadata to those stored data points so that we can always reuse data that came from earlier calculations or that came from databases. And we find that that's a really useful thing. A useful thing to think about is you don't want to just store all your data in some sort of comma delimited file. You want to actually have attributes associated with each of those points so you can track down why those points are maybe unexpected. So that's another aspect of, I think, data set management for machine learning. We have a series of, I think the last thing I was talking about is we have a series of ways of deciding if a calculation is actually good and suitable for going into a machine learning model versus ones that are, you know, not so good and shouldn't be learned. So that's another aspect of it. That's a big challenge for us in open shell transition metal chemistry and materials in general, is that the data quality, it's a lot harder to assert that you definitely have good quality data as opposed to closed shell organic molecules.
Yeah, maybe I can add, yeah, that for really beginners, like because I think we all have to teach some courses about machine learning now in the universities. So for my students, I designed like very simple data sets, even like this H2 dissociation. It's kind of, it seems to be simple, but when you try to apply different kinds of tricks and test different strategies, then students learn a lot. So and these data sets and how to train and so on the website, in the links I showed. So this we have some tutorials for students. They're openly accessed. You can play with them if you're just starting, so it's kind of useful.
Thank you. Then another question for Professor Kulik concerning the case you showed for the search for catalyst for methane oxidation. Your approach predicts structures for possible transition states. What is the criterion for choosing the best catalyst candidates?
Yeah, so the two properties we were optimizing were release of the products and hydrogen atom transfer. For hydrogen atom transfer, what we did was we used the reaction energy. So we avoid doing transition state selection in the active learning. But then on the Pareto optimal catalyst, we then computed the transition states explicitly, which we only need for the hydrogen atom transfer step and the oxo formation step. But our goal, because hydrogen atom transfer follows such a strict BP relation, our goal was to, if you make the thermal more favorable for hydrogen atom transfer, you also make the activation energy more favorable. And then for release, it's just desorption. So our goal was to make the desorption not too uphill and make the hat sufficiently downhill.
Okay, thank you very much. Then I think I'll maybe stop here because we're running out of time. I'm sorry for the people whose question I could not ask yet, but I'm sure we're all very motivated to learn more and hear more about it, and we'll have many future opportunities. So I would like to thank the speakers again and the attendees, and maybe now go over to Xiao.
Thank you.
Thank you.
Thank you very much for the very nice discussion. I really enjoyed this panel. Thank you, Eva, as well, for moderating it, as well as to Professor Eder, Pavlo, and Michele for the very kind participation and engagement with the attendees on answering most of the questions that we have addressed. So I want just to finalize, or before closing, to highlight some of the activities that we have been organizing in the scope of the International Younger Chemists Network webinars. So the one that we started this month, right at the beginning, was the Science Cafe on highlighting the top 10 emerging technology in chemistry that IUPAC has been releasing since 2019 on an annual basis. And some of them, for instance, have been highlighted in 2020, such as the RNA vaccines that were awarded very recently with the Nobel Prize in Chemistry. So this is really very important and showcase to the public the importance of chemistry, since some of these technologies are at the early stage of their discovery, others are more close to being fully commercialized. So this is quite appealing. And we have started with this series of cafes that will highlight some of these technologies by inviting speakers working specifically in specific topics. And the next cafe will be taking place in September. So please keep an eye on the IYCN social media channels for the further information on how to register for these further events, and for getting further information on the speakers that will be joining us on the occasion. Beyond that, I would like just to highlight that we are now having a new project. So besides this one of the ChemVoice, we are having this new project on global conversation on sustainability with the IUPAC that has been just very recently released, and you can just go into the website. But basically what we want to aim is to engage with all of you globally in the conversation on sustainability. What actions are you doing locally, or what should be done in your opinion to target specific SDGs that are pressing in your countries? And what we ask you is that if you want to join us in this conversation, you can just go to the website, and we highlight some of the possible events that we can plan on your own, such as a panel discussion, a lecture series. And then after you register your event at the website, then on the September 25th, if you organize it virtually, we can promote it via our social media. And we want then also to keep track of your event, what was the feedback of the people, what were the main conclusions, because we want also to then write some follow-up articles and organize symposia by next year via the follow-up of these events taking place this year. So we want to of course highlight and to implement sustainable practice among the chemistry community worldwide, to foster the communication among people nationally, internationally, to pursue this sustainability practice, and also helping in targeting the SDGs that are quite close. The target of 2030 is quite close. And also we want to promote actions for the benefit of society on the overall terms and well-being of human beings, but also for sustainability of our planet. And of course, we want to, with this project, to launch also collaboration among people through this exchange and the knowledge that will be gathered and fruitful discussions during the event. So please have a chance and have a look into the website for more information on this project. And also just to show you a video, I think the sound will not, I don't know if it will run. So we want really this to be a call of action and to join us. So this will be very important to pursue sustainability and sustainable practices for our future, but also for the future of the next generation that will be suffering from actions that we will not be taking today. So please have the chance, and if you have any questions, you can also email us at the IYCN@iupac.org, or if you want to contact us directly through this project, the email is contact@gcs-day.org. Please feel free to do so. And so with this in mind, I would like just to thank very much to all the speakers. So we have really a great lineup of speakers, great talk, great panel discussion, speakers from all over the world. So it was they were very kind in joining from different time zones and adapting themselves to join us. So thank you very much once more. Thank you as well to Eva for coordinating also the panel, and also to all of you that are within the audience that took the time to join and engaging, and also for raising very nice questions that for sure enriched our discussion with this great lineup of speakers. So with this, I would like just to thank you once more to all of you for joining and for taking part of this webinar, and see you soon. Please keep track of these events and also social media channels and website of IYCN for further events. Thank you very much, and have a nice weekend, everyone.